Welcome! In this session, we'll explore problem number 159, titled Longest Substring with at most two distinct characters. This problem challenges our understanding of substring manipulation and efficient algorithms. Let's dive into the details and solve it together. In this problem, we are tasked with finding the length of the longest substring of a given string S that contains at most two distinct characters. The input is a single string S, which consists only of lowercase English letters. The output is an integer that represents the length of this longest substring. For example, if the input is S equals ACEBA, the output would be 3, since the longest substring with at most two distinct characters is ECE. Here's another example to clarify the problem. If the input string is S equals KABAB, the output is 5. This is because the longest substring containing at most two distinct characters is AB, which has a length of 5. Now, consider a simpler case where S equals A. Since the string contains only one character, the longest substring is the entire string itself, resulting in an output of 1. To further solidify the understanding, let's go over some constraints and edge cases. The length of the input string, S, is guaranteed to be between 1 and 100,000 characters, and it will only consist of lowercase English letters. For edge cases, if the string contains only one type of character, such as AAA, the result is simply the length of the string. If there are exactly two distinct characters, like in ABABABAB, the entire string is the valid result. On the other hand, if a third distinct character interrupts the substring, as in ABAC, the valid substring ends before the third character, resulting in a length of 3 for ABA. Lastly, an empty string is not a valid input due to the constraints. To solve the problem of finding the longest substring with at most two distinct characters, one approach we can consider is the brute force method. This approach is very straightforward in its intuition. We check every possible substring of the string S to see if it satisfies the condition of having at most two distinct characters. For each substring that meets the requirement, we calculate its length and keep track of the maximum length encountered. While the steps are simple, it involves iterating over all possible substrings, counting distinct characters in each, and updating the maximum length. This method comes with significant drawbacks. Generating all substrings already takes n squared time, and counting distinct characters in each substring adds another n, in the worst case, leading to a total time complexity of n cubed. This makes the brute force approach impractical for larger inputs due to inefficiency and redundant recalculations. A more efficient strategy is to use the sliding window technique combined with a hash map. This approach eliminates the need to examine all substrings by dynamically maintaining a window that contains at most two distinct characters. The key idea is to use two pointers, left and right, to define the bounds of the window. As the right pointer moves through the string, we add characters to the hash map and update their counts. If the hash map contains more than two distinct characters, we shrink the window by incrementing the left pointer and removing characters from the hash map when their count reaches 0. At each step, we calculate the window's length and update the maximum length if needed. This method is much more efficient because both pointers traverse the string only once, making the total time complexity n. Additionally, operations on the hash map, such as adding or removing characters, are 1 on average. While slightly more complex to implement than the brute force approach, this method avoids redundant work and is well suited for large inputs. An alternative to the hash map-based sliding window is to use a fixed array for character tracking, which can be particularly useful when the input is limited to lowercase English letters. Instead of a hash map, we use an array of size 26 to store the frequency of each character in the window, and a separate variable keeps track of the number of distinct characters. The overall process remains similar. We adjust the window using two pointers and update the maximum length as we slide through the string. This variation also achieves n time complexity since the pointers traverse the string once, and array operations are constant time. The main advantage of this approach is its slightly faster performance due to the fixed size of the array. However, the drawback is that it is less general and only works with predefined character sets, such as lowercase English letters. For problems that require handling broader character sets, the hash map approach remains more versatile. The optimized sliding window with a hash map is ultimately the chosen strategy due to its balance of efficiency, generality, and clarity. By leveraging the sliding window technique, we dynamically adjust the substring boundaries to ensure that we always have at most two distinct characters, avoiding unnecessary computations. The use of a hash map allows us to handle any character set, making this approach robust and applicable to a wide range of scenarios. Additionally, the sliding window ensures that each character is processed only once, leading to a time complexity of O(n). While the fixed array approach may be slightly faster, its limitation to specific character sets makes the hash map solution more flexible. The real insight here is recognizing how naturally the sliding window aligns with the problem constraints, focusing only on valid substrings and avoiding redundant calculations. This strategy achieves O(n) time complexity and O(k) space complexity, where k is the number of unique characters tracked, which is constant in this case, as we only need to handle two distinct characters at any time. The problem we are tackling is to identify all substrings within a given string that meet a specific condition. They must contain at least a certain number of distinct characters, denoted as k. This is a common challenge in areas like DNA sequence analysis, where distinct patterns are critical, or in log analysis, where unique tokens might convey meaning. The most straightforward way to approach this is the brute force method. Here, the intuition is simple: we generate every possible substring and check whether it satisfies the condition. To break this down, we initialize a counter to keep track of valid substrings. Using nested loops, we consider all possible starting and ending indices of substrings. For each substring, we calculate the number of distinct characters, often using a set since it automatically eliminates duplicates. If the size of the set meets or exceeds k, we increment our counter. Finally, after all iterations, we return the count. While this approach is intuitive, it becomes computationally expensive as the string length increases, making it important to explore optimizations. To address the inefficiency of the brute force method, we can use the sliding window technique. This approach eliminates the need to recompute properties for overlapping substrings by dynamically adjusting a window over the string. We start with two pointers, start and end, that define the window. A frequency map, implemented as a dictionary, is used to track how many times each character appears within the window. As the end pointer expands the window, we update the frequency map. If the number of distinct characters in the window exceeds k, we increment the start pointer to shrink the window until the condition is met. For every valid window, we count all substrings that begin with the current start and end at the current end. This ensures that we efficiently count substrings without redundantly examining every possible combination. The process continues until the end pointer reaches the end of the string, at which point we return the total count of valid substrings. One of the key insights here is how we manage distinct character counting. In the brute force approach, using a set simplifies the process of identifying distinct characters, but this comes at a cost because the set needs to be recomputed for every substring. The sliding window method, on the other hand, avoids this recomputation by dynamically updating a frequency map as the window changes. This distinction makes a huge difference in efficiency. The brute force approach has a time complexity of O(n) cubed, because it examines all possible substrings and calculates distinct counts repeatedly. The sliding window method significantly improves upon this, reducing the time complexity to O(n), as each character is added and removed from the window at most once. Additionally, it's important to handle edge cases carefully. For example, if the string is empty or if k is greater than the length of the string, there are no valid substrings. When all characters in the string are identical, the frequency map simplifies the counting process. For large values of k, we can even optimize further by terminating early when the window size becomes smaller than k. The choice of data structures plays a critical role in the efficiency of these algorithms. In the brute force method, a set is used to calculate distinct characters in each substring. While this is straightforward, it becomes inefficient due to repeated computations. In the sliding window method, a dictionary serves as a frequency map, allowing for dynamic updates in constant time. This makes it possible to adjust the window size without recalculating distinct characters from scratch. Additionally, the two pointers start and end are integral to the sliding window approach. They enable us to efficiently define and adjust the boundaries of the window, ensuring that we only process each character a limited number of times. These data structures work together to reduce redundant computations and achieve the improved time complexity of the sliding window method. Finally, let's analyze the complexity of these approaches. The brute force method has a time complexity of O(n) cubed. This arises from the nested loops used to generate all substrings and the set operations that compute distinct characters for each substring. The space complexity is O(k), where k is the size of the set storing distinct characters. On the other hand, the sliding window method achieves a time complexity of O(n). This is because each character is processed at most twice, once when it is added to the window and once when it is removed. The space complexity remains O(k), as we use a dictionary to store character frequencies. Overall, the sliding window method is significantly more efficient, especially for longer strings, making it the preferred solution for this problem. This implementation solves the problem of finding the longest substring with at most two distinct characters using the sliding window technique, which ensures efficient processing of the input string. Here's a step-by-step explanation. 1. Data structures. A dictionary char_map is used to store characters as keys and their most recent index as values. This helps us efficiently manage the distinct characters in the current window. 2. Sliding window. Two pointers, left and right, are used to define the boundaries of the sliding window. Right iterates through the string, adding characters to the window. 3. Add characters. For each character at index right, it is added to char_map with its index. This ensures the dictionary keeps track of the most recent occurrence of each character in the current window. For check distinct count, if the size of char_map exceeds 2, i.e., more than two distinct characters, the algorithm identifies the leftmost character in the window, using min char_map.values, and removes it from char_map. Subsequently, the left pointer is moved to exclude the removed character from the window. 5. Update maximum length. After each iteration, the length of the current window is calculated as right-left plus 1, and max_length is updated with the maximum value observed so far. 6. Output. Finally, max_length is returned as the result, representing the length of the longest substring with at most two distinct characters. This approach ensures efficient processing with a time complexity of O(n), where n is the length of the input string, as each character is processed at most twice, once added and once removed. The space complexity is O(1), since the dictionary size is limited to two distinct characters. Here, we start by importing the necessary classes and defining our solution class. Inside the class, we create the method length of longest substring toDistinct, which takes a string s as input. The goal of this method is to find the length of the longest substring that contains at most two distinct characters. To achieve this, we use a sliding window approach along with a hash map to keep track of the last occurrence of each character in the current window. We initialize the left pointer to 0, which will represent the start of our window, and max length to 0, which will store the maximum length of the valid substring encountered so far. Now, we iterate through the string using the right pointer, which represents the end of the window. For each character, we add it to the char map and update its position to the current index. If the map size exceeds 2, it means the window contains more than two distinct characters. In this case, we find the leftmost character in the window by identifying the minimum value in the map, which corresponds to the earliest occurrence. We remove this leftmost character from the map and adjust the left pointer to exclude it, effectively shrinking the window. After adjusting the window, we calculate the current window size as right-left plus 1 and update max length if this size is greater than the current max length. Finally, after the loop completes, we return max length as the result, which represents the length of the longest substring with at most two distinct characters. This implementation efficiently handles the problem using the sliding window and hash map approach, ensuring that we achieve optimal performance. The overall time complexity of this solution is O(n), where n is the length of the string s, as each character is processed at most twice, once when added to the map and once when removed. The space complexity is O(1), since the size of the map is limited to two distinct characters. With this, the implementation is complete, and the method is ready to be used to solve the problem. We begin with the input string isiba. Initially, the character map is empty, and both the left pointer and the maximum length are set to 0. At the first step, when the right pointer is at index 0, we add the character e to the map, associating it with its index. The window now contains only one distinct character, which is valid since the limit is 2. We update the maximum length to 1. Next, when the right pointer moves to index 1, we add c to the map. The window now contains two distinct characters, which is still valid. Therefore, we increase the maximum length to 2. Now, at index 2, we encounter E again. Since E is already in the map, we simply update its index. The window remains valid with two distinct characters, so we update the maximum length to 3. At index 3, we add B to the map. This introduces a third distinct character, making the window invalid. To fix this, we remove the leftmost character, which is C, and adjust the left pointer to the next valid start index, which is 2. At index 4, we add it to the map. Again, the window becomes invalid due to 3 distinct characters. We remove E, the leftmost character, and move the left pointer to 3. Finally, the maximum substring length for this example is 3. From the previous calculations, the output for the first example is 3. Now, moving to the second example with the input string kebab, the initial setup remains the same, an empty character map, and both the left pointer and maximum length set to 0. At index 0, we add C to the map. The window has one distinct character, so we update the maximum length to 1. At index 1, we encounter C again. We update its index in the map, and the window remains valid with a maximum length of 2. At index 2, we add it to the map. The window now contains two distinct characters, which is valid, so we update the maximum length to 3. At index 3, we encounter it again and update its index in the map. The window remains valid, and we update the maximum length to 4. At index 4, we add B to the map. This brings the total distinct characters to 3, making the window invalid. To fix this, we remove C, the leftmost character, and adjust the left pointer to index 2. At indices 5 and 6, we process two consecutive B characters. We update the index of B in the map, and the window remains valid with two distinct characters. The maximum length is updated to 5. For this example, the output is therefore 5. Now, let's analyze a simpler edge case where the input string is a. In this edge case, the initial setup is the same with an empty character map and both pointers at 0. At index 0, we add it to the map. The window contains only one distinct character, which is valid. We update the maximum length to 1. Since the string has only one character, the output for this edge case is 1. The time complexity of this solution is O, n, where n represents the length of the input string. This efficiency is due to the fact that we only iterate through the string once using a for loop, which contributes O, n. Inside the loop, each operation is designed to be constant time. For instance, adding or updating an entry in the char_map dictionary is an O1 operation on average. Similarly, checking the size of char_map is also O1, since its maximum size is limited to just 3 entries, 2 distinct characters and 1 extra before the sliding window adjusts. Even finding the leftmost index by calculating the minimum of up to 3 values is O1, as the dictionary has a constant size. Adjusting the window by removing entries from char_map and updating the left pointer are also O1 operations. Lastly, the sliding window approach ensures that each character is processed at most twice, once when expanding the right pointer and possibly again when adjusting the left pointer. This guarantees a total of O2n operations, which simplifies to O(n). The space complexity of this solution is O1, which is constant and independent of the size of the input. This is because the char_map dictionary, used to store character frequencies, has a maximum size of 3. It only ever holds entries for 2 distinct characters and 1 extra before the sliding window adjusts. Since this size does not grow with the input string, it contributes O1 to space usage. Additionally, all other variables such as left, right, max_length, and leftmost are scalar values and occupy fixed space regardless of the input size. Together, these factors ensure that the total space usage remains O1, making the solution very efficient in terms of memory. When comparing the optimized sliding window approach to a naive solution, the difference in efficiency becomes clear. A brute force method would involve generating all possible substrings of the input and checking each one for distinct characters. This would require O(n²) substrings to be generated and, for each substring, counting the distinct characters would take O(n) in the worst case. This results in an overall time complexity of O(n³). In contrast, the sliding window approach eliminates the need to generate substrings. By using a dictionary to track distinct characters dynamically, it reduces the time complexity to O(n). This optimization makes the solution scalable for much larger inputs. When analyzing the best, average, and worst cases, the algorithm consistently processes each character at most twice. In the best case, where the string contains 2 or fewer distinct characters, the algorithm finishes in a single pass, running in O(n) time. For average cases with random strings, the window adjusts occasionally, but the time complexity remains O(n). Even in the worst-case scenario, where the string alternates between more than 2 distinct characters, each character is still processed at most twice, ensuring O(n) time. To mathematically prove the big O time complexity, consider the behavior of the sliding window. Each character in the input string is added to the window at most once when the right pointer expands. If the distinct character constraint is violated, the left pointer adjusts the window by removing characters, ensuring that each character is removed at most once. This means that for an input of size n, the right pointer performs at most n operations to expand the window, and the left pointer performs at most n operations to adjust the window. Together, this results in a maximum of 2n operations overall, which is linear. Therefore, the time complexity of the algorithm is conclusively O(n). When tackling this problem, there are several common mistakes to watch out for. First, not handling edge cases, such as an empty string or a single character string, can lead to runtime errors or incorrect outputs. For example, if S is an empty string or just contains one character like a, your solution might fail unless these scenarios are properly accounted for. Always test your implementation with minimal input sizes to ensure correctness. Another mistake involves inefficient substring generation. Using nested loops to generate all possible substrings, especially when counting distinct characters, can result in solutions with O(n) cubed complexity. These approaches can quickly time out on larger inputs, so it's essential to use optimized techniques like the sliding window. Additionally, counting distinct characters inefficiently, such as repeatedly converting substrings to sets, can add unnecessary overhead. Instead, maintain a dynamic frequency map or array to track character counts efficiently. Finally, watch out for off-by-one errors when indexing substrings. These small mistakes, like including an extra character or skipping the last one, can lead to incorrect results. Testing boundary cases thoroughly can help catch these issues early. Now, another area to be mindful of is ignoring constraints on the character set. If the problem specifies a limited alphabet, such as lowercase English letters, you can optimize memory usage by leveraging an array of fixed size, like 26, rather than using a dictionary. This small adjustment can significantly improve performance. Shifting to interview insights, recognizing patterns in substring problems is crucial. Many of these problems require optimizing brute force solutions with techniques like the sliding window or prefix sums. Being able to identify when a sliding window approach is appropriate is a key skill during interviews. Optimal space usage is another important consideration. For instance, if the character set is fixed, arrays provide constant space efficiency. On the other hand, if the character set is larger or unknown, a dictionary might be necessary. It's also important to evaluate complexity trade-offs. A sliding window with a frequency map is typically O(n) in time complexity, but it does use extra space. Discussing these trade-offs transparently with your interviewer demonstrates a thoughtful approach. Lastly, clear communication is essential. Make sure to articulate how you're handling distinct character counts and edge cases in your solution. This problem also shares similarities with several related problems, which can help you expand your understanding and sharpen your skills. For example, longest substring without repeating characters, LeetCode problem 3, is a classic problem that uses similar sliding window techniques. Minimum window substring, LeetCode 76, explores substring properties in a different way, focusing on finding the smallest window that meets certain constraints. Longest substring with at most k distinct characters, LeetCode 340, is a direct extension of this problem, generalizing the concept to allow for any number of distinct characters, not just 2. Subarrays with k different integers, LeetCode 992, brings a new twist by focusing on subarrays rather than substrings. Exploring these problems will help you spot recurring patterns and apply the right approaches efficiently. Speaking of approaches, the sliding window technique is often the most efficient for these types of problems because it runs in O(n). However, it requires careful handling of the window's resizing and the frequency map to ensure correctness. Another option is prefix sum with hashing, which is useful for problems involving cumulative properties, although it's less intuitive for problems that require counting distinct characters. Finally, dynamic programming is another approach to consider, especially for variations involving overlapping subproblems. While it is more complex to implement and debug, dynamic programming can be particularly effective for problems that involve global optimizations or overlapping substrings. For example, if the problem requires combining solutions to smaller subproblems or making decisions based on previous states, dynamic programming might be the best fit. Keep in mind, though, that this approach can be more time-consuming to set up and may introduce additional space complexity. Understanding the trade-offs and knowing when to apply each approach will not only improve your problem-solving skills but also help you stand out during coding interviews. Great job! We've successfully solved problem number 159 and reviewed key concepts like the sliding window technique and hash maps. Keep practicing these patterns, they're invaluable for interviews. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!